previous video reminded me that I probably should touch on the difference between spring and neap tides, therefore all of the different factors that go into impacting what the magnitude of the tide will be, as well as the different types of tides that there are. So I would hope you already know that the tides are caused by the moon, the gravitational impact that the moon has on the oceans, pulling the oceans towards it whenever it's overhead, or just either when it's overhead or when it's on the opposite side of the earth, just causing like hydraulic effects that will pull the water outwards from the earth a slight bit and then let them fall back later on during the cycle. But what people don't necessarily know is that the sun also plays a factor there as well. Because the sun's so much farther away, even though it's so much larger, the moon has the much greater impact on the tide than the sun does. I think it's like 80-20 the moon to the sun. But the sun does still play a role, meaning the alignment between the two has an impact on the strength of the tide. So if this is the Earth and we put the moon here, the way the tide looks like, if you zoomed out onto a global scale, obviously this is highly exaggerated, is that the tide bulges out on both sides of the Earth, both the one side closer to the moon and the side opposite of the moon, just equal and opposite forces. It pulls in the low on the sides of the Earth that are kind of 90 degrees offset from the direction of the moon. By the way, let's say this is the North Pole here, so you're looking down on the Earth from above. So we'll pull it out in this hemisphere, pull it out in the opposite as well, and then squeeze it in on these two. So you've got high tide here, low tide there and there. And that's why as the Earth rotates, you'll have usually 4 total maximums in a day. 2 highs, 2 lows. Now what a spring tide is if the moon and the sun are in line, this is going to get highly accentuated because obviously both of them are acting with one another. So it's going to pull these highs out even higher, and as a result pull these lows in even lower on both sides. Meaning during a spring tide, when the Earth and the sun are in line, or the moon and the sun are in line with one another, it will make both maxima more extreme, higher highs, lower lows. A neap tide occurs when the moon and the sun are at a 90-degree angle, meaning the moon's pulling the water this way, the sun's pulling the water this way. What that does is it smooths out the curve to the point that, I don't know if I drew this well enough, but it is still definitely higher here and here. Like these still are higher tides than the datum, and these are still lower tides than the datum, but they're much less significant. During a neap tide, the highs are relatively low and the lows are relatively high. How often we go between a spring tide and a neap tide, or somewhere in between the two, goes into the revolution of the sun around of the Earth around the sun, and revolution of the moon around the Earth. So it's pretty, on the outset, it's difficult to predict this in advance. It's actually all very consistent. If you had a strong enough mathematical model, you can predict this out forward in time, meaning it's not actually necessarily that difficult. Another factor that could come into play is seasonality and the tilt of the Earth that might bring certain areas more in line with the moon, which might shift it. Like if the Earth tilted so that the moon was relatively up here, it might shift the highs over there. Things such as that. The geography of a given area also plays an impact. If your seabed is really, really shallow like this, Obviously, for the water to move from this level up to this level is going to involve a very large distance to go, and so it might take longer just because it's filling a larger volume, as opposed to a steeper beach like that where it would only need to fill up to there, meaning that the duration of the tide might change, and the height as well. All of these factors come into play, influencing how, like, what the cyclical nature of the tides will be, which is why intuitively it's difficult to predict, but technically all of these can be broken down mathematically to the point that you could understand when it's all going to be very, very accurately, actually, which is what the tide tables do. Now, there are 3 types of tides: diurnal, semi-diurnal, and mixed. And this just refers to how frequently that a high and a low tide occur. So a diurnal tide, let's say this is the length of a single day. A diurnal tide only involves one full wavelength in a day, as in a single high tide and a single low tide. A semi-diurnal tide in one day has 2. So 2 high tides, 2 low tides. These are obviously the most common. This is what everyone thinks of when they think of, the way tides work. They know pretty common knowledge that there are 2 high tides in a day, 2 low tides in a day. I don't know, 70% of the world works like this. There are some areas, I think places in Louisiana have diurnal tides. It's relatively rare, but it does happen. A mixed tide occurs when, presumably a mixed tide is usually also diurnal. But it looks something like that, where there's 2, not presumably, it's always semi-diurnal, but the maximums in a mixed tide are not relatively close. In a semi-diurnal system, this high tide and this high tide are pretty close to the same height, and same as these lows. In this one, the first high is much higher than the second high. The second low is much higher, or much lower than the first low. It doesn't always have that exact pattern, but it is offset. It's not, they're not similar to one another. Every single height of tide is not unpredictable, but just looking at it, you wouldn't be able to tell how high or low the next one is based off of the previous. This is also relatively rare. I think more common than diurnal tides. And there are parts of, I think, like the Bay Area of California has mixed tides. But once again, the vast majority are semi-diurnal.